This is Module 8C from my Introduction to Tensors for Non-Mathematicians online video series. This module specifically is titled MATLAB Demonstration of Linear Map Theory. In this module, we're going to explore how the linear map theory from the last two lectures may be implemented in MATLAB. Can we use MATLAB to verify that a linear map, for example, yields the same primal vector output both before and after an appropriate change of basis is applied? How do we write that code? How do we translate this theory to a MATLAB script? I think many of you will enjoy this very hands-on video. I have written a text to accompany these lectures. A link to that will be placed in the description when it's available. Still working on publishing. As always, I look forward to reading your questions and potentially corrections in the comment section below. Please share. So let's jump into this code. Let's jump into this MATLAB script. You'll note that this lecture is structured a little bit differently from some of the others. A lot of our other modules, a lot of our other lectures, we're going through PowerPoint presentations with a very clear structure and let's say, progression of the topics. Here in this lecture, we're going to be doing something that's different, right? We're going to be taking a look at this MATLAB code here on the right side of the screen. And so this is MATLAB code that's included in the text. Again, still working on a link to that, but when it's available, you can download the text with this script. Now, this script I am going to provide to you separately in the comment section, but for the other topics, such as the bilinear form, the scripts are not going to be included unless, unfortunately, you purchase the text. So the structure here is different because we're going to be trying to explain this script here on the right-hand side, and the reason why I have PowerPoints to the left is because, we'll want to refer back to those at certain points to sort of show, on the left side, what theory we're focusing on, and on the right side, how we implemented that theory using MATLAB. So I think this will be really useful to those of you that are looking to bridge that gap between understanding the theory of tensors and then actually implementing them for some useful application in either MATLAB or Python. And we're not going to be using too many complex libraries, so we're not going to be using PyTorch or TensorFlow. This is really just going to be building tensors as basic algebraic structures. Okay, so why don't we jump into the code here. First things first, I always clear the memory. I always clear the screen. The comments here are pretty decent, so if you're taking a look at this on your own, hopefully you'll be able to understand. And again, look in the description below for a copy of the MATLAB code. Okay, so let's generate two primal vectors, an input and an output primal vector, and then let's define a linear space to relate them, and then we'll play around with some transformations and sort of demonstrate that all the theory we presented earlier actually works. So first thing, we want to define the system. Now, we are going to employ random numbers to generate our system, including the input coordinate array, which is V in A, the input and output basis sets B in A and B out B, as well as the linear map type tensor, which we call 10M. These will be used to verify the theory from our notes. Okay, so let's define the coordinate array for the input. And if we look here at the slides to the left, what we are actually defining is what's referred to as vcol over here, right? This is the coordinate array for some sort of primal vector, specifically for the primal vector that's serving as the input. Now, this is a three-dimensional case, so we have three elements, unlike what we see to the left here. That's a two-dimensional case, so I guess this would actually be closer to this example where we have V, no arrow hat, with three different elements. And then we are going to define the primal basis of both the input and the output vectors. So essentially, we have B in A, that would be this basis set here that's associated with the input coordinate array, and then we're also generating something for the output. Now note that we have not, I'm going to type something new in here, right? We have not defined the output coordinate array yet. We're going to rely on the linear map to do that. Okay, Couple other things. Now, we are going to at some point need the inverse of the output. Actually, we did this for both, for our basis sets. So you can see we define beta in A as the inverse of our input basis set, and beta out B as the inverse of the output primal basis set. Now, why do we call this beta? Because if you remember in the notes, we referred to the inverse of the primal basis set as a dual basis set. We use the letter B. We associate that with a primal basis set, and we associate beta with a dual basis set. So as we take the inverse here, we are changing from the representation of B to the representation of beta. So again, still, we're just defining our system. Next, we're going to define our tensor M. Now, this is different from the coordinate matrix that we're going to talk about below. So the coordinate matrix will be referred to as MAT, or matrix coordinate M. And again, we're going to use random numbers. So since our input and output primal vectors are both dimension 3, that means that our tensor will similarly have to have a contravariant rank of 3, contravariant size of 3, meaning 3 rows, and a covariant size along that single rank of 3. So essentially a 3 by 3 algebraic object of rank 2. So I apologize for what I said a second ago. It's contravariant rank 1. It's covariant rank 1. It's overall rank 2. But the size along those individual ranks is 3 and 3. Okay. So next, we want to calculate the coordinate matrix that's associated with this tensor. Why? Because we want to demonstrate that the theory we presented earlier works. Again, this is really just a demonstration of our theory for the sake of verifying it. So previously, we talked about how to calculate the coordinate matrix, and now we want to implement that. So I brought up the appropriate slide over here. We talked about this in the linear map lecture. Unfortunately, this is a little bit small, so perhaps I have to make this bigger. All right, let's make this a little bit bigger. And so what you can see here is that the coordinate matrix associated with our tensor, which is everything inside of these larger parentheses, is equal to the inverted output basis set times the tensor times the input basis set non-inverted. So if we go over here, okay, try to make this a little bit smaller, you'll see that this is the equation we have right here. So we're calculating the coordinate matrix associated with the tensor as the product of the inverted basis output basis times the tensor times the non-inverted input basis. And note that this right here we could also call beta out B. So we're going to run this stuff near the end. I think it'll make more sense for us to go through the code, look at how everything works, and then we can run certain pieces and sort of check to see that it's working the way that we expect. So now, recalculate tensor M. What's going on here? So what I want to do is I want to take our coordinate matrix associated with our tensor, which is MAT coordinate M, and I want to recreate our tensor, which is called tensor M, using some theory from our notes. Specifically, I want to use this right here. All right, I want to demonstrate that this equation works. We have some tensor M, we have some coordinate matrix that is defined in terms of these bases down here, the non-inverted output basis set times the inverted input basis set, and then we multiply by the appropriate basis here and here. Now you may ask, well, wasn't this inverted previously and the pre-A was non-inverted? And yes, that is true, but you have to remember previously what we were trying to do was calculate the coordinate matrix from the tensor, and down here we're calculating the tensor from the coordinate matrix. So it makes sense that they would use, one would use an inverse in place of the normal value, or vice versa. All right, so what we want to do is we want to recreate our tensor. And in order to do that, we're going to use this summation form of the tensor taken directly from the PowerPoint that we looked at as part of the linear maps module. So what do we have to do to create our tensor? We're going to take this sum. We're summing over two iterative variables, right? Because we have to worry about our contravariant and covariant indices. So we take the appropriate index of the coordinate matrix that's coming directly from up here, defined with respect to the appropriate basis. And we're multiplying that by the tensor product of the mth output basis, primal output basis, and the kth, okay, element of the inverted input basis set. And now we're referring to it as beta because instead of talking about a column, right? Generally, when we talk about a primal basis set, we're looking at a column, hence the subscript covariant index. Now we're talking about a superscript contravariant index because, right, the basis covectors for the dual space are going to be row oriented. And so we index that using a superscript. And so that's best demonstrated by this slide from the linear map module. So what we see is that the primal basis set is composed of column-oriented vectors in a row-oriented set, right? So we use a subscript to index an individual vector within the primal basis set. For the dual vector, the dual basis set, it's the opposite, right? We have individual row-oriented covectors that are arranged, they're stacked vertically. So we use a superscript in order to index the appropriate one. And like we said previously, when we invert a primal basis set, specifically the B sub pre A, when we invert the primal basis set, we can represent that as a dual basis set and index that in the similar way. Okay, so let's go back to the slide we were at. So again, we're trying to use this form right here within our MATLAB code in order to rebuild our tensor. So let's see if we can do that. All right, so again, we are going to have to cycle through both the contravariant and the covariant indices. So we have k equals 1 to 3 and m equals 1 to 3, right? We're generating our tensor using the vector-covector basis pairs as shown in equation 54, right? That's referring to the text, but in the PowerPoint, it's this right here. Okay, so the equation, pretty easy to set up. The tensor is equal to the tensor. The reason why that is because we're adding new elements with each iteration. So this is essentially just a running sum. And then right here is what we previously looked at. So we have the appropriate index of the coordinate matrix times the kth basis of the output basis set, and then the mth basis from the inverted input basis set, which now looks like dual. Now, unfortunately, at least the way I have MATLAB set up, I can't separate the contravariant and the covariant indices. So generally, at least for this rank 2 example, I'm always going to consider that the contravariant index is first and the covariant index is second. So it makes sense that we're indexing the output basis set with a subscript or a covariant index, and we're indexing the input using a contravariant or a superscript index. All right. And then what I have right here is a message that's essentially just telling us whether this worked or not, right? It's comparing the tensor that we generated initially, right? This is our ideal value, and it compares it to the one that we recalculated. And so actually, I think this is a good place. I'm going to go back on what I said previously. And let's go ahead and just run the code. So I'm just going to define tensor m equals tensor m, and then tensor recalc m equals tensor recalc m. And so by running this, we should expect to see those values be the same, and we should also expect to get this success statement right here. So let's see if we can get this up and running. Okay, editor. Sorry, 1 second. All right, so let's run this. Okay, add to path, that's fine. And if we look down here, we can see that, yes, success, we observe that the original tensor that we generated is the same as the one we recalculated. So, nothing new here. We're just demonstrating that we can decompose our tensor, or we can convert our tensor to its coordinate matrix form using the basis, and then we can use this equation to reverse that. So yeah, so that worked great. All right, so let's move on. Next, we want to calculate the output from the tensor as well as the coordinate matrix. So next, what we want to do is we want to calculate the output, which is a primal vector within a primal space, from the tensor as well as the coordinate matrix. So we have our tensor here. We could use either one of these values because we have agreed that they're the same. And we have the matrix, the coordinate matrix for the linear map, which is right here. And we can calculate the output using either. Now, how do we do that? Let's slide back over to the slides for a second, to the PowerPoint. What we see is, right, this is taken directly from, again, that linear map module. So we know that vector B is equal to the linear map tensor times vector A. So this, and it's shown up here, this is the equation that we would use to calculate the output VB from the input VA as well as its tensor, which is represented by 10 sub m. Now, we can also calculate that using just the coordinate matrix. So if you remember in this slide, we moved our output basis set over to the right hand side, and we ended up with this piece here, which is the coordinate matrix. And that's what we had called, if we go up here, mat coordinate m. So that is what is represented right here. So we can calculate the coordinates of the output from the coordinates of the input using the coordinate matrix. Notice that the basis is not associated with it. Or we can calculate the output tensor from the input tensor and the linear map tensor. We can do it in terms of primal vectors, or we can do it in terms of coordinate arrays. And we expect to get the same answer, or at least the same answer once we account for the basis. All right. So this section calculates the output generated by the linear map and input vector VA product using both the tensor and matrix-based expressions, which we just talked about. It then compares these values to ensure they match. So just to take a quick side note, because I know I've talked about the text, these are the types of matrix MATLAB scripts that we include in the text. And I mean, I'm trying to do my best here to present it in PowerPoint, but as you can see, it's really better read. So I want to throw a quick plug in there. Please check out the text if you want more MATLAB scripts like this. I think it's very helpful for understanding. Okay, so first things first, we want to calculate the output from the product of two tensors, then convert it back to the coordinate array. So what we're doing right here is we are essentially implementing this equation. Sorry, it keeps changing my spot. All right, so we're using this equation right here. VB, primal vector VB, is equal to the tensor times primal vector VA. Okay, so, right, tensor out B, V1 is just a version number to help us separate things, is going to be equal to the tensor M times vector A. And that's why you can see it's the basis set times the coordinate input. And we'll get a result here. Next, what we're doing is, and I can add a note in here, we are calculating the coordinate array associated with the output tensor. Remember, this is our VB arrow hat, by essentially dividing by the basis set associated with it, right? We know that the coordinate array associated with the output is equal to the vector divided by or times the inverse of the basis set. So right here we have the output tensor, and here we have the output coordinate array. Now we expect this to match what we calculate when we use this form right here, right? If we're taking our input coordinate array and multiplying by the coordinate matrix, we expect to get that same coordinate output. All right, so now we're calculating it the second way. So this is the alternative method, perhaps we could call it that, alternative. Okay, so the coordinate array is equal to the coordinate matrix times the input coordinate array. You can see here there's no basis involved in that equation. And then we're calculating the tensor as the product of the basis and the coordinate array we got above. So here it's sort of doing the same thing forwards and backwards. So here we calculate the tensor, okay, the primal vector output from the input, and then we go back and we calculate its associated coordinate array. Then over here what we're doing is we're calculating the coordinate array from the input coordinate array, and then we are calculating the tensor associated with it. Now we expect this value to match this value. They're both tensors, primal vectors, and we expect this value to match this value because both of those would be the coordinate arrays associated with it. So what we did was I calculated the difference between those values. Both of these should match. Okay, both of these should give us a 0, and right, we again will do a quick check, so we expect to see the success here. So what I'm going to do is I'm going to remove these semicolons, which will allow us to see the answers, and then I'll put a pause here, although I need to remove my previous pause. Okay, so I'll get rid of that. All right, so now let's run this again. Now you'll note the answers are not going to turn out to be exactly the same. We are randomly generating the numbers each time, and that's just so we can make the script a little bit more robust. Okay, so I'm stopping this. I'm going to save. I'm going to rerun. Now what do we end up with? Okay, so first things, we end up with the tensor as 0.17, negative 0.22, okay, and then down here we have 0.17, negative 0.22, 0.007. So the tensors, they do agree with one another, great. And the coordinate arrays, negative 0.32, negative 0.39, negative 0.92, and that matches the values down here. Okay, the deltas that we calculate are both very small. Okay, those are essentially calculation errors. And we end up with success, essentially meaning that the two ways that we calculated the output in this little chunk of code right here both generated the same answer, so they do agree with one another, which is good. Okay, so the next thing we're going to talk about is how to apply a transform to a linear map, but I did want to quickly just look at this slide one more time and make sure that everybody who's viewing understands the difference between the linear map type tensor, its associated coordinate matrix, and then the basis set for that linear map, which is defined by the tensor product of the output basis and the inverted input basis sets. Okay, but let's move on to the transforms. So we know that we can define two matrices. So we need to define separate transforms for the input and output primal vectors, or the primal spaces. They could be the same, but they don't have to be the same. So we define that as f pre-A post A. Okay, and that gives us the transform between the pre-transform basis and the post-transform basis for both the input as well as the output. So A corresponds to input, B corresponds to output, and then the opposite applies to the coordinate arrays, right? The forward transform matrix actually takes us from the post-transform coordinates back to the pre, or we could use the backwards transform matrix here. So if we look in our MATLAB, we'll see we have F pre-post A and F pre-post B. They're all randomly generated. So these would be 3x3 transform matrices that we have to apply to, we have to use to transform both the vectors, the primal vectors, as well as the linear map. And then we went ahead and defined their inverses as well. All right, now here, what we're doing is we are transforming our inputs. So V post A is equal to the inverse of our forward transform matrix times the original. Now, I didn't use the subscript pre, but whenever you don't see the subscript, that would be where the pre would come in. Okay, and so this would be analogous essentially to this equation right here, and then below it would be analogous to this guy. And you can see we're taking the output coordinate vector that we calculated previously and using that. So this is dealing with a coordinate array. Sorry, I called that coordinate vector, and this is also a coordinate array. Okay, and then now we can do the same thing for the basis sets over here. Okay, so, and I think I may have misspoken a second ago, but let me restate it. So this equation is actually analogous to this right here. I think previously I said it was this. I apologize. So this equation is analogous to this one. This equation is analogous to this one. Scoot over a little bit here. All right, this equation is analogous to this one. And, well, actually, it would be the inverse. And this equation is analogous to this one. So what we're doing in this section is we are calculating the post-transform values of the input and the output primal vectors in terms of their individual components, the coordinate arrays, as well as the basis sets. Okay, so now what we want to do is we want to apply the appropriate transform to the linear map coordinate matrix as defined in equation 62. Now we're not using the book, we're using the PowerPoints. So let's find the appropriate equation. Sorry, PowerPoint keeps resetting my place in the PowerPoint. So we can see here, I think this is the slide. Well, we could use either one of these. We could use this slide right here. So what we see is that we have our matrix initially in terms of the pre-transform basis. And then over here we have the matrix in terms of the post-transform basis. In order to achieve that transform, we need to apply the inverse of the output forward transform matrix. So that would be the inverse of this guy right here. And then we need to multiply by the non-inverted or actual transform matrix associated with the input. Trying my best with the language here. I know it can get a little bit hairy, but hopefully by demonstrating and bringing it back to the notes, we can clear up a lot of confusion. Okay, so this equation here is merely an implementation of what we had on the PowerPoint slide. Now, you'll see that we also applied the same transform, but using the summation form. And so if we go back over here to the slide, that's merely just this form down here. Okay, so we can calculate individual elements of the transform of the coordinate matrix, the linear map coordinate matrix, by taking the sum of the products as defined here. Now, I think in that previous lecture I talked about how this is equivalent to this. I'm not going to go through and discuss that now. But anyway, so we want to implement this equation as well just to make sure that it works. And so I'll let you compare on your own. But what we're doing is we're cycling through both the covariant and the contravariant indices. We're initializing each element of the output coordinate matrix to 0, okay, when we begin. And then what we're doing is we're taking the initial value, we're adding it to itself. Why? Because again, we're taking a running sum here. We need to do this for all the elements. And then this piece right here corresponds to this right here. Okay, I don't think I can get them both on the screen. Let's see if I can, maybe. All right, let's see. All right, so what we can see is we have B, post B, pre-B, and the indices are K and B. Okay, K is the superscript, B is the subscript. Then we multiply by the coordinate matrix before the transform with superscript index B, subscript index A. Okay, again, I said the first one is the superscript. And then we have F pre-A, post-A, with the indices A as the superscript and M as the subscript. All right. So what we expect there is for this coordinate matrix to be transformed. We did it in a matrix form. And then this to be the transformed matrix, but we just did the same thing in the summation form. And then here, again, what we're doing is we're checking to make sure that these are the same. And for the purposes of demonstration, you know, we can put them, we can show their values here really quick just to see that they give us the same thing. Now, again, I know some of you may be watching and saying, well, this is pointless. I mean, it is. It's pointless in terms of getting an actual result, but it's useful, not pointless in terms of demonstrating you know, how the theory works. Okay, so what we expect is for these two values to be the same and for this to give us a success indicator. All right, let's try running this one more time. Again, this code is available in the description of the video. Okay, just want to make sure that the other pause was gone. All right, so we're right down here, so let's run this again. And well, the first promising thing is we got a success. Okay, that's good. And then you can see here we have we have the coordinate matrix associated with the linear map transformed. Up above is how we transformed it using the coordinate, the transform matrices, and down below was the summation form. So again, nothing unexpected there. All right, so now let's take this a step further. We have demonstrated that we can build, well, we can define a linear map type tensor. We can calculate the coordinate matrix from the tensor, and then we can also use that coordinate matrix and recalculate the tensor, and the values match. That's good. Okay, then what we showed is we could calculate the output as both a coordinate array directly using the coordinate matrix, okay, or we can calculate it as a tensor using the linear map type tensor. And that was what we showed in the last 2 sections ago. Then what we showed, and this was the most recent subsection of the code, that we can apply a transform, which is taken directly from that applied to the input and output primal vectors, and we can transform our coordinate matrix. Now we can do so either using the tensor, or the matrix form, or we can do it using the summation form. Now, I think one last thing that we want to demonstrate is that the output, right, that we get should be the same regardless of whether we use the pre or the post transform tensor. Okay, because actually the tensor doesn't change pre or post transform. It's only the coordinate arrays and the coordinate matrix that changes. Okay, so we have that right here. So we want to calculate the output from the transformed matrix. I'm going to get rid of this real quick. And we want to make sure it matches that which we got previously. So we calculated it 2 times previously. They were up here. So here we have V out B, V out B. We have tensor out B, tensor out B. So these will change. Okay, the coordinates will change because we applied a transform to them. But we don't expect the primal vectors to change. So that's what we're going to compare down below. All right, so first thing we're going to do is we are going to calculate our output, which is called V post B, and this is right after the transform. We're going to calculate that using the transformed coordinate matrix as well as the transformed input coordinate array. So that's the equivalent of essentially we are looking at using this process right here. Okay, so we are calculating the output coordinate array from the transformed coordinate matrix times the transformed coordinate array. All right, so no basis involved here. Now, what can we compare this to? I'm actually going to compare it in 2 ways. I'm going to add one thing in here. First, we can compare it to this, right? We already took the answer, the coordinate array that we generated further up above right here. Okay, we know that to be true. We verified it to be true. And then we transformed that using the transform matrix, okay, appropriately. So what we expect is that this value will match V post B. And that is what we have right here. That's what we're checking for right here. But I'm going to add one additional line. We can also check it in terms of the tensors. So I'm just going to call it VB or tensor VB version 4. I don't really know what notation I want to use here, but I just want to define a tensor. And we know that that should be equal to the coordinate array. So V post B version 3, okay? And we can multiply that by the basis set. Okay, we have to use the post transform basis set. And so that would be that right there. So we can calculate the tensor that's associated with it. And we expect this to match all the other tensor values that we got previously. So I can just pick any one of those. Okay, I'll pick this one right here. And we expect these values to also be the same. So I don't think there's any need to have a pause here. All right, but before we run this code right here, you may have noticed there was a cut in the video. That's because initially the values didn't equal, and that's because there was a mistake in the code up above. Right here, I was calculating the post transform output basis in terms of the inputs. It didn't have an effect on the original answer because we weren't performing this check, but this was originally the wrong value. Anyway, so what we're doing is we are comparing the output coordinates from this equation right here. We're comparing it to what we got previously. If we get success, that's a good thing. However, we can also compare the tensors. So we can take this new coordinate array after the transform, multiply it by the, again, post-transform basis, and we expect to get a tensor that's invariant to change of basis. So whatever we get right here, we expect it to match the tensor values that we calculated up above from somewhere right around here. Okay, and so let's go ahead and run this. And what we see is first success. Okay, these two coordinate arrays do equal one another. And then we can also see that these tensors, which I've highlighted, they also agree with one another. So, I mean, that's pretty much it as far as this MATLAB script is concerned. I like to do things like this, where we look at theory and implement it in MATLAB code and kind of calculate things, calculate their inverse. I think it's a really good way to demonstrate your knowledge of a topic. And again, really isolate any misunderstandings that you may have or any mistakes. So unfortunately, I won't be able to do too many more of these MATLAB videos. Again, it just takes a lot of time. And I am trying to reserve some of the resources to encourage people to buy the text. But this is an example of the kind of analysis, the kind of MATLAB example that you can expect to see in the text if you choose to purchase it when it's available. Again, sorry for the delay there. So I hope you all enjoyed this. The link to the code is in the description below. And the next module is going to dive into some other interesting topics. We're going to talk about maps versus forms, as well as moving on to the bilinear form, which is a new tensor type. So the linear map, right, maps one primal vector to another primal vector. The bilinear form, we'll see, is going to map two primal vectors, or the tensor product of two primal vectors, to a scalar value. And that's one example of applying the bilinear form would be the metric tensor. All right, so we'll cut it there, and I look forward to your comments and questions and potentially corrections in the comment section below.